So, ladies and gentlemen, thank you very much for joining us to this one more Athena talk. It's a great pleasure to have with us Professor Graham Turnbull from the University of St. Andrews, or from the physics department. There are many reasons why we have invited, Graham Turnbull, to this series of talks. One of them is like a friend. It reminds me personally very good memories that I had as a master's student and PhD student a long time ago in University of St. Andrews, and the very beautiful and friendly to the students city of St. Andrews. Graham, I'm going to start with his education. He has a master with honors from the University of St. Andrews, a PhD from the University of St. Andrews in the topic of CW optical parametric oscillators. He's a senior member of the IEEE, fellow of the Institute of Physics since 2019. He has demonstrated a pioneer work in the fields of organic semiconductors, light-emitting diodes, and lasers, photonic applications of soft materials, applications regarding nanophotonics, plastic lasers, and chemical sensing. His work has received more than 7,300 citations, and his H index is 44. Part of this pioneer work is like the latest, outcomes of the St. Andrews group regarding a milestone. And it is a milestone that, they have demonstrated electrically driven organic lasers. And this electrically pumped is like, I think, one of the biggest technological advances regarding this topic. Graham will tour through his work in the next 40 minutes. The title of his work is Electrically Driven Organic Laser Using Integrated Organic Light Emitting Diode Pumping. So the floor is yours, Graham, and thank you once again for your contribution despite of your busy schedule. Thank you.
Well, that's great. Well, thank you very much, Kostas, for the kind invitation to talk to the Athena network. I'm very pleased to say something about some of the recent work we've been doing, and some of the background that's led up to that historically in the area of organic semiconductor lasers. So to start off with, though, I'm going to just highlight that this is not only my work, but there's a large team of people who've been working over the years in St. Andrews on this research topic, and I list many of them, hopefully all of them on this slide. The people highlighted in white, Ko Yoshida, Jin Yigong, Ivor Samuel, are the key people that have been contributing alongside myself to the place where we're going to finish the talk with electrically driven organic lasers. And I have made Alex Kanabolowski and Peter Skabara, who are chemists from the University of Glasgow, honorary members of St. Andrews University, for this slide, who made the materials on which our breakthroughs have been reliant. So, but to start off with, I'd like to go back to a historical point when Kostas and I were PhD students in the late 90s. This was my understanding of what an organic laser looked like. So this is an organic liquid dye laser. It's a very complex piece of optical equipment that has mirrors and prisms and a jet of liquid organic dye passing through the cavity as the gain material. And so these are very sophisticated lasers that can generate very precise wavelengths, and you can tune them smoothly over wide ranges. There are also lasers which require a large footprint. So in this lab here, there's a picture of the dye laser on the left, and an argon ion laser, which is a 2-meter long gas laser that was needed to optically drive the dye laser. So these are big systems. At about the same time in Cambridge, unknown to me at the point I was a PhD student, the first solid-state organic semiconductor laser was made, and this was made by Nir Tesla and Richard Friend in a semiconducting polymer that was one of the materials they were studying for some of the early OLEDs, organic light emitting diodes. And so this device is a little microcavity between a silver mirror on one side and a dielectric mirror on the other, with a very thin film of the organic semiconductor in between. And so this opened up a possibility that you could make organic lasers in a much more simple way and much more compact way, and also the possibility that you might be able to electrically drive them in the way you could make an organic LED. And so the aim of my talk over the next 40 minutes is to talk a bit about the strategies that we've been looking at to try to miniaturize organic lasers from these big tabletop systems down to something that's very, very compact and ultimately electrically driven. Now, there are some challenges, and there's some reasons that this has taken a lot of years to get to the point where the field has got to, and that's because direct electrical injection into the organic semiconductor, it's very difficult to achieve a population inversion and lasing in that case due to various reasons that I'll come to as I go through the talk. And so our strategy has been not to directly inject, but to make integrated systems where we separate spatially the electrical injection and the population inversion in order to avoid some quite intractable or at least very challenging problems. So let's take a step back to organic semiconductors. So organic semiconductors are a special class of plastic materials and thin film amorphous molecular films that have some quite unusual properties. So plastics are normally electrical insulators, but these materials, because of the particular bonding arrangement between adjacent carbon atoms, have electrical semiconducting properties, and they can also be stimulated either optically or electrically to emit visible light. And so because they are molecular solids with a skilled chemistry colleague, you can tune the properties by changing the chemical structure of the material. We can solution process these, which means that we can make printed electronic devices, and it opens up possibilities to make a completely different set of optoelectronic devices from the kind that are usually made with silicon or 3-5 semiconductors. And so this shows a couple of examples. So the organic semiconductors, now many of you have several million OLEDs in your pocket in the display of your mobile phone. And so these are very much mainstream optoelectronic devices and systems. This is an example of a future flexible organic solar panel that is very lightweight and so could be hung on buildings and generate efficient electrical power from the sun. So what about for laser materials? So organic semiconductors are also quite interesting as laser gain media because their energy level systems are amenable to making a broadband 4-level gain medium, where we go between 2 electronic states in the molecule and a series of vibrational sub-levels within each electronic state that allows us to make a 1, 2, 3, 4-level laser gain medium, where we optically excite on one transition, and then the excitations relax to the lowest level of the first singlet exciton state, and then we can achieve stimulated emission on this red transition here. Organic semiconductors, however, also have a manifold of both singlet and triplet exciton states, and the triplets normally cause problems. They're troublesome triplets because they will not emit light, but they will absorb light very often at the wavelength you're trying to amplify. The other nice thing about organic semiconductors is the molecules are engineered so you can have very efficient light emission at very high chromophore density, which lets you make small lasers. They have very strong optical transitions, and so that you can get high optical gain in a very compact laser structure. And associated with that, we have typically nanosecond fluorescence lifetimes, which does mean we need to optically pump them or electrically drive them very hard in order to create that population inversion and sustain it. Because they're plastic light materials, we can simply process them. We can make very high quality, optical quality thin films. We can nano pattern these with grating structures. But one of the challenges we have with these materials is that they do not cleave easily to make a nice facet at the end of a polymer waveguide. And so that tends to mean that we need to work with a slightly different geometry of laser resonator from that's normally used with semiconductor lasers. So this is the sort of typical common resonator structure that's used in an organic laser. So in a conventional laser, you have a gain medium in the middle and you have two mirrors at either end, and the light travels backwards and forwards between the mirrors through the gain medium to build up the laser field. In this case, what we do is we embed a diffraction grating into the side of our polymer waveguide, which as light travels through the waveguide, it gets diffracted by the diffraction grating. And very often we choose a period of grating such that a first order diffraction will provide a surface emitted output beam from the laser, while the second order diffraction reorients the wave through twice the angle and provides the in-plane feedback within the film. And so these are distributed feedback lasers. As well as a one-dimensional structure, you can also make two-dimensional photonic crystal structures, or you can even make structures where you have concentric circular gratings providing feedback all around some magical central point. So there's ranges that we can do, and we can nano imprint these structures in a very simple way. So in order to drive our organic lasers, we need to think about how we pump them, how we create this exciton population in the upper laser level. And so what we need to do is we need to establish a high density of exciton excitations in the gain medium. And so if we are optically pumping, then typically we need to use a laser that's emitting ultraviolet, blue, or green light, usually with nanosecond pulse durations or shorter, because we need to be able to establish the population inversion before fluorescence depletes the upper laser level, but also to try to make the laser switch on before the triplets build up and start to add losses to the gain medium. This means that we need to work with very high irradiance, and so in some cases I will often talk about the laser threshold, the pumping requirements to get the laser to switch on in terms of kilowatts per square centimeter or watts per square centimeter, or sometimes we'll talk in terms of microjoules per square centimeter. Or if we're electrically driving, then we need to look at the possibility of a current density to achieve this high excitation density in the film. So what about moving from an organic light emitting diode, which is a very successful technology, to an organic injection laser? So to think about this, first of all, it's useful just to introduce what is the generic structure of an OLED. So an OLED is a planar thin film device in which we have an organic layer or molecular layer, often actually multiple layers of different molecules serving different electrical transport and optical properties in the device. So we have a series of organic layers that are sandwiched between typically a metal electrode on one side that injects electrons and a transparent conducting electrode on the other side that injects holes into the device. The overall thickness of the however many organic layers we have in this structure is typically in the order of 1 to 200 nanometers in total thickness. So they're very, very thin structures. So what about if we want to, instead of just generating electroluminescence, generating light, what about if we want to create the population inversion, optical gain, and laser action? So this is a very challenging thing to do. And the reason is that we based on our optically pumped lasers, we know that we're going to need typically in the area of kiloamps per square centimeters injected current into the device. And this is difficult because the charge carrier mobility in organic semiconductors is very low. It's orders of magnitude lower than in 3-5 semiconductors, such as gallium nitride or gallium arsenide. And the consequence of that is to get a high current density, you need to have very high densities of charges in your device. The high density of charges start to interact with your excited states, and they can either deactivate the excited state by quenching the light emission, or they can introduce additional absorption, extra loss mechanisms in your cavity. And so that causes a problem and raises your threshold. In order to have a low operating voltage, you also need to keep your contacts close together, and so you end up with potentially losses from the metal contacts. And in addition to that, we inevitably generate a large number of non-emissive triplet states when the electrons and holes recombine, and they also will quench the light emission and quench the light emitting process and also absorb light. So this is all very difficult, and so people have looked in the field for 20, 25 years to try to get over many of these problems, and many of these problems along the way have been solved or addressed in one way or another. And so, but the best that the community has been able to do so far was this work from Chihaya Edachi's lab in Kyushu in Japan about 5 years ago now, where they gave reasonable evidence, but didn't tick all the boxes for direct electrical injection of an organic semiconductor laser. And so they had a structure which was similar, that they have two electrical contacts, one above and one below the organic semiconductor layer. They embed a grating to provide the feedback, and then they electrically drive this. And so this device showed many of the signatures of laser action with a narrow spectral signature and a change in the light emitting characteristic as you increase the drive current to the device. But it was not able to show a very well defined laser beam from the device, and it didn't last for very many pulses, because we're in this sort of structure, in this sort of approach, you're really stressing these organic semiconductor materials to do many things all at the same time, and they found that the device would only run for a few tens of pulses before it would stop operating. So it's a very difficult thing to do and to do successfully. So our approach has been to take a slightly different path through this, to look at indirect electrical driving of the organic lasers. And so we started this journey a long time ago, looking at just making very compact optically pumped lasers. So microchip laser is like a pulsed version of a green laser pointer. And so these are quite successful and compact. Or you can use as the blue diode laser, the gallium nitride diode laser technology started to get better, then people found that they eventually became strong enough to be able to optically pump the organic laser. But in both these cases, you need another laser to drive your organic semiconductor laser. So about 15 years ago, we did some initial work looking to see if we could use gallium nitride LED technology to pump the organic laser, and I'll show you a couple of our older results of that in a moment. This is quite a big challenge because it's difficult with a light emitting diode to get a very high power density, number of watts per square centimeter, into the organic semiconductor. And so it takes quite a lot of careful design physics and the device physics to get that to work. And more recently, we've managed to make a fully integrated structure where we essentially embed the laser's gain medium into the substrate of an OLED and directly drive it in an all organic device. And that's where we're heading in this talk. But this is even more difficult because you're quite limited in the total power you can produce and the power density. So what does an organic laser look like? So this is an organics surface emitting distributed feedback laser here. It's based on a two-dimensional feedback grating that's providing the feedback in the plane of the film and a beam emitted out the surface. It has a slope efficiency of say typically 10% and a threshold of a few kilowatts per square centimeter. And so it can emit a nice output beam. The cross shape in this output beam is determined by the shape of this of the feedback structure in the grating. So in these distributed feedback lasers, the grating controls everything. So the period of the grating determines the wavelength. So the wavelength is related to the refractive index of the waveguide times the period of the grating. The symmetry controls the beam shape and the polarization of the emitted beam. And the in a more subtle way, the shape of the repeat unit of the grating and its overall size controls the threshold and the efficiency. So if we want to go to ever more compact and simple pump sources, then we need to drive the threshold density that gets the laser to switch on ever lower. And so the part of the trick is in the grating design. So we spent many years trying to make very low threshold organic lasers for diode pumping. And one trick you can do is you can try to change the shape of the periodic structure by changing the duty cycle of the width of the valleys to the widths of the peaks, and that can allow you to drive down the threshold. Another approach, which was initially proposed by Lemmer's group in Karlsruhe, was to make structures called mixed order grating structures. You take a periodic structure and then you sandwich it between two other regions with half the period. In these very short period structures, you only get in-plane feedback and no surface emitting output loss, output coupling, so lower output loss. And then you control the amount of output loss by this second order grating region, where you can, by changing the length of this overall grating section, you can control the amount of output coupling loss. And that can drive you down to a few tens of watts per square centimeter of light emission, with the light being emitted only from this region here, this sort of 5 micron long region of the device. There's another approach that we have settled on as our preferred way to make very low threshold feedback structures, and that's to use what we call a substructured grating. And so here we take a second order grating, which is a surface emitting structure, and we essentially make two replicas shown by lines B and C, which are slightly offset in position from each other, so that we end up with a periodic structure that has two teeth in every unit cell. And by changing the separation of these teeth within the unit cell, one can actually have huge control over the feedback and the relative amounts of feedback and surface loss in the resonator, which allows us to achieve both efficient output coupling over a large area but keeping thresholds very low. And so this allows us to get down to, again, only a few tens of watts per square centimeter, with a surface emission over a large area, say over a millimeter sort of length scale, which means you can get a collimated beam out from a device that's got very low threshold. So thresholds are low. Why do we need thresholds to be low? So if we want to not laser pump our laser, but we want to use let's say an LED, then there's some advantages and some challenges. So the advantages: this is compact and it's electrically controlled, and so it's moving towards an electrically driven laser, but in discrete components. But it has some challenges, that it's incoherent light, so it's hard to focus and concentrate, and whatever optics you sit in front of your LED, the best you can do is get typically 30 watts per square centimeter continuous wave. You can do better if you pulse, but that's typical maximum power density out of inorganic LEDs. And so to scale the power in blue LEDs or white LED lighting, you just make them larger. So we found, however, that if we drove these LEDs with sort of nanosecond duration pulses or tens of nanosecond duration pulses, we could drive them up to kilowatt per square centimeter type power. So this takes us into the range where you can optically pump the organic laser. And so this was our first attempt at this, where we took a Luxian, Lumiled's Luxian LED. We took off the plastic dome lens, replaced it with a plastic light emitting DFB laser, and drove it very hard with current pulses. And so this first laser, about 15 years ago, just managed to squeak above threshold, and we got this typical characteristic where you get this higher slope appears and a narrow peak starts to appear in the spectrum, showing the onset of lasing. With some further work, we were able to make these a bit more robust, and this is work from that was carried out by Georges Siminis and Christina Wong at the time, where we could get a nice green laser beam being emitted out of our organic semiconductor laser that's pumped by an LED. So that's LED pumping, but there's still some challenges. So this shows the typical characteristics, where now we have a few hundred watts per square centimeter threshold. So this has gone up from the low values that I just had previously mentioned, but we get a nice single frequency laser emission. And we can see temporally that when we drive the laser, we can drive it above. This shows the pulse of the light emitting diode, and this shows the laser pulse that switches on a little while after the light emitting diode has started pumping the device. Now, the reason that these thresholds are higher, we had to think about a little bit, because if we compare the same laser device pumped by either an LED or by a laser of the same wavelength and same excitation area, we find that the laser-driven organic semiconductor laser has a threshold that's about a fifth of the LED pump structure. Now, everything is the same in this experiment except the pulse duration. And so what we discovered was that actually if you need to be able to switch your LED on very, very fast, because this relatively slow rise over the course of 10 nanoseconds even allows triplet states to build up in the device that adds extra loss, which increases our laser threshold. And so it's crucial that you can modulate the light on and off very, very fast in the drive LED. So what I want to do now is I want to move on to using the OLED for optical excitation. And so OLEDs, as I mentioned before, are in most new mobile phones. You'll have a million red, a million green, and a million blue OLEDs in that device. They are very efficient. They can have brightnesses in the displays of 1,000 candelas per square meter, which though that corresponds to less than a milliwatt per square centimeter output power. And so for using an OLED to drive the organic laser, we need to go into a completely new regime of very high intensity operation and very short pulse operation. And so over the years, we've been trying to drive LEDs into this very fast and intense operation. And this is work by Ko Yoshida and Jinyi Gon in my group. And so just to show the scale of what we need to do, though, is here's our typical standard everyday organic semiconductor laser using this substructure grating. We need to get sort of OLED outputs of 100 watts per square centimeter to drive this laser above threshold. However, the field of pulsed organic LEDs wasn't in the right place. the best that anybody had ever achieved before we started working on this project was about 25 watts peak power density per square centimeter. And so this was somewhat too low to be able to drive a laser. And so Co and Pavlos Manasiadis have spent some time trying to engineer and make very fast organic LEDs for a different application. We've been interested also in using OLEDs as Li-Fi sources, so sending optical wireless data transmission very fast. And so in order to do that, you need to be able to modulate your OLED on and off very fast. And so Co spent a lot of time engineering the organic LED. Here's the organic layers between metal contact and transparent contact, to engineering these OLEDs in order to minimize their RC time constants, maximize the speed at which the light emission takes place, maximize the speed at which charges travel through the device. And in doing so, he was able to get to devices where he could modulate them on and off at hundreds of megahertz. And this allowed us to data encode, in partnership with Harold Haas's group in Strathclyde, gigabit per second data links using a single OLED transmitter. And so taking some of the technology that we've developed in fast OLEDs, we aim to use this as our engine for the organic laser. And so the idea here is that we take a blue OLED that's based on this molecule here, TSBF, which has a short lifetime and a good spectral match to our best organic semiconductor gain material, and we engineer the device to have a PIN OLED structure that lets us reduce the series resistance of the device. We engineer its shape to allow us again to minimize RC time constants and maximize injection of light into the gain medium, and we engineer the thickest contacts anybody's ever thought to make on an OLED to try to fight against series resistance. And so this is the device stack that we finally got to after quite a lot of work on Co's part. So this shows our light emitting layer in purple between some charge transport layers that are doped to be very low resistance on either side. We have a thick opaque cathode that acts as a mirror to send light always downwards through the device, and a semi-transparent anode. And there's also a lot of engineering in the plane of the device, and so we have two contact wires that come into the thick opaque cathode, which runs along as a long stripe in the light emitting part of the device, and then we make the thin transparent anode as short a path length as possible to make a rectangular shape that will generate the electroluminescence. We actually fabricate this whole device on a carrier glass sitting on top of a thin barrier layer, thin film barrier layer structure. We detach the whole device, which is only about 5 microns thick in total, maybe 10 microns thick in total, off the carrier glass, and then place that onto the laser. So this shows the OLED performance, where we're driving with few nanosecond pulses of current, and we're getting a light emission out that has up to about 45 watts per square centimeter light from the surface of the OLED. So this is not the 100 watts per square centimeter we need, but we're getting part of the way there. And the way we get the whole way there to drive the laser above threshold is that we have to carefully and completely integrate the laser into the OLED substrate. And we do that because by integrating the laser gain medium into the OLED substrate, we avoid some of the total internal reflection losses that you have in the glass, and we estimate through calculations that we can increase the radiant excitance to the radiance to the gain medium by a factor of about 2 to 2.5, which gets us enough to potentially go above threshold. So we integrate our organic laser, DFB laser, into the substrate of our OLED, and we do this, and then we optically drive with very short current pulses into the OLED. And when we do this, we can drive the laser above threshold. So this is a log-log plot, and this shows our electroluminescence spontaneous emission part of emission from the device at low current densities, and then above about 3 kiloamps per square centimeter, we can drive the laser above threshold. And the laser emits a single frequency emission that we can identify as being on a photonic stop band edge of the distributed feedback structure. So we've characterized also the output beam from this laser device, and we find that this shows the intensity through a polarizer as you rotate the polarizer analyzer angle, and we can see that as we rotate the polarizer from 0 degrees to 90, we have a very high polarization ratio of the emission above threshold. It's still polarized light below threshold, but that's characteristic of the grating structure and the waveguide, but it becomes much more strongly polarized when you go above threshold. We also see that from below threshold, this shows the beam emitted onto a camera at about 2 centimeters from the laser. Below threshold, we have some structure that comes from the grating embedded in the waveguide. Above threshold, it comes down to this small narrow beam of light being emitted. This double-lobed pattern of the beam is characteristic again of a surface-emitting DFB laser. And then we look, as we move the camera progressively further away from the laser, we see that we have this well-defined beam that's gradually diverging in the direction perpendicular to the grating grooves and diverging a little bit more along the grating grooves, again typical of the resonator structure that we are using. So we've got a nice, well-defined laser beam and all the characteristics of a laser. We find also that this device will last for of the order 10 to the power 5 pulses before the OLED decreases in power by about 5 to 10%, and the laser threshold increases by a similar amount, and then we drop just below threshold. But there's lots of scope to extend that into many millions of pulses and beyond. So one thing that we don't have a good handle on, or as yet in this talk, is what's happening inside the gain medium. So we know what electrical drive we're putting into our integrated device, and we know what light's coming out. And so to interpret that, what we've done is we've looked at a study where we both electrically drive the organic laser and simultaneously optically pump the laser at the same time, and we look at the balance of optical power and electrical drive that's needed to get the laser to switch on. And this allows us to understand more of what's going on inside the gain medium. So here's a different organic laser, electrically driven. So under electrical drive, we have a threshold in this case, in this device of about 5 kiloamps per square centimeter, where we move from just electroluminescence, from essentially an LED to laser action. And so what we're going to do is we're going to electrically drive the device at 4 different levels below laser threshold. So 3 at below laser threshold, then we're going to just switch the electrical drive off, which falls off the end of my log-log graph, and to see how much additional optical pumping from an OPO, a nanosecond OPO, we need to drive the laser above threshold. So if we electrically drive quite close to but below threshold, then we find we need very little additional optical pumping to drive the laser above threshold. As we reduce the amount of electrical drive, we need progressively more optical pumping to to get the laser above threshold. And so from this, we can look at the amount of drive we're using from our OLED against the amount of power, additional power you need from the OPO, from the laser, to pump the laser, the organic laser above threshold. And from this, we can estimate that the peak irradiance from the OLED that will make the device work under only electrical drive is around 95 watts per square centimeter. And so that's 2.4 times higher than what we can emit from the OLED into air, but that's in good agreement with our calculations of the enhancement you get by tightly integrating the electroluminescent layer and the gain layer together. So that brings me to the end of the presentation. What I've hoped to try and give you is some of the design requirements that you need to do in order to miniaturize these organic semiconductor lasers, and how that's allowed us to move to this exciting development where we've made these integrated electrically driven devices. So we just attach two wires and we get laser emission out. So this, however, is opening up needing to open up necessarily a new area of operation for OLEDs, and there's various new challenges that we're now looking to solve. Organic LEDs don't normally run under these very fast, very intense driving conditions, and actually we think that the microscopic physics in the materials is somewhat different, and we don't fully understand that yet. And so that's an area that really needs some study, and we're very excited to be starting to do that. The actual devices themselves, to take them through to application, there's certainly, we've got them above threshold, but there's more work to do to make them more efficient operation, and there's strategies we have now to improve both the electrical drive and also the optical properties of the resonator to drive up the efficiency of these devices. And then there's a constant need in all organic semiconductor research for great chemists to develop the new materials. And so the best in the world OLED materials are no good for organic lasers. Now we need new materials that are going to work in this very different region of operation. And so with that, I shall finish my talk and say thank you very much for your attention.
Thank you very much, Graham, for this very nice presentation and very informative, I will say, and very well explained. I would like to open the floor for questions. I have some questions, and usually I'm starting. I don't know. I'm going to start the discussion then.
Okay.
The first thing that I would like to ask you, Graham, is like, what about how much the bandwidth of your output beam is narrowed beyond the threshold? So beyond the threshold, we have seen these graphs that you can calculate the threshold level, but spectrally, when the lasing starts, what is the stringing? What is the spectral purity of the outcome of the output beam?
So when we have a distributed feedback laser such as this structure, so if we have just a planar film, then we get essentially Lambertian emission pattern coming out with a cosine of the angle dependence in intensity. With the diffractive structure, we already get some level of directionality in the beam, and that somewhat depends upon the properties of the grating, to what extent these diffracted peaks dominate over the Lambertian background. In this case, we're looking at, and this both affects the spatial but also the spectral dependence. So here it's not the world's greatest graph to show it, but here we have a very broad emission that is extending over. This is only showing 50 nanometers of bandwidth. The actual emission from the molecule is maybe 50 or 60 nanometers wide. The diffraction grating will pick out a couple of peaks that correspond to the band edges of the photonic stop band. I'm afraid I haven't got the right slide in the stack to show you that better today. Above threshold, we find that this laser peak rises up. Typically, it's 0.1 nanometers wide, limited by the resolution of our spectrograph, and so that's typical for these pulse lasers. We could probably work harder to narrow it further, but that's not something we've tried to do.
I mean, I think that the periodicity of the grating does not affect the landwidth. Affects the wavelength for sure, but I think that the number of lines also affects.
So that can affect it. So there's people often talk about the Q of their resonators. I tend to the Q of the resonator certainly it increases as we have the increased number of lines. Once you're above threshold, then there's other coherence questions of the amount of sort of coherence noise or phase noise in the stimulated emission process. And I think that probably is the thing that somewhat limits that's kind of more the limiting factor on the line width, that we're only pumping for a few nanoseconds. We don't we don't try to very carefully control the line width, and so we end up with sort of order 0.1 nanometer line widths.
Graham, my second question is is there any possibility of fine tuning, these kind of devices, or the wavelength is locked because of the material and the grating properties?
We can tune these in. So in this device, I think we're currently somewhat locked because we're trying to optimize other things. In the wider field of organic semiconductor lasers, there are a few ways that people will tune them. So these devices can be on flexible or stretchable substrates, and so you can actually mechanically tune the grating period.
Yes.
We've also looked in the past at thermal tuning of the structure, and so the organic semiconductors typically have a negative thermoelectric coefficient, and so you heat the structure up, and the refractive index drops, and so you will blue shift the wavelength. So there are some opportunities for tuning in those ways.
Thank you very much. I have another question that I have is what about the profile of the output beam? What about the transversal mode? Do you observe something like 10-0-0 or?
So if we look at the output beam here, so this is for a grating where the grooves are running horizontally in this diagram. The grating grooves are running horizontally in the diagram, and so perpendicular. So this is for a one-dimensional grating. The emission pattern that if we look going across the grating groove, so if I look down this green line on the diagram, typically for a surface emitting distributed feedback laser, you have two lobes. So it's kind of like a 1-0 mode in that dimension. We actually do very little in confining the laser beam in the other direction, in the direction along the grating grooves, and that's something that we know we need to do better on when we try to do other things. So we're interested in, for example, in trying to drive towards continuous wave lasers in these materials for the first time. And then we know we're going to need to confine this beam and manipulate the beam in a cleverer way. And so it's pretty highly multi-mode in one dimension. In the other dimension, it's pretty close to a 1-0 mode. And the reason it has a dark phase in the middle is to do with the standing wave mode in the waveguide, and how the standing wave mode relative phase of the standing wave mode compared to the physical grooves in the grating is such that essentially the traveling wave that's going this way and the traveling wave that's going this way that together make up the standing wave, when they are diffracted out, they diffract out to have destructive interference right in the middle of the beam, and they only have partial destructive interference at the edges, which leads to very little light in the middle, and then these two lobes on either side. But you can change that by engineering and sort of phase slips in the grating, for example, to make it single mode and to make it pretty much a good Gaussian beam, at least in one dimension, and then with some better lateral confinement, you could take it to a much higher quality lower M squared beam.
This is indeed, and during your presentation you compare, and this was a very nice, I would say, experiment that you compare how much optical pump you need to have depending on the electrically pump. So you have the contribution from electrically pump and optically pump device. So you would like to check, what's happening within your gain media.
That's right. Yeah.
I mean, what about the efficiency? How the efficiency varies between optically pumped lasers and electrically pumped organic lasers?
Okay.
The efficiency of the device.
So our device efficiencies, which you'll find in the paper, are quite low. So these devices are this first attempt was basically in the regime of sort of microwatts per amp slope efficiency, which is very low, and we know we need to improve it significantly. But actually, that comes partly because the laser cavity that we had was very much optimized to minimize thresholds, and so we've not got the optimum output coupling on this laser yet. And so I think that's one area where we can do better, and we know that we can get 10-15% slope efficiency out of an optically driven laser. The other thing that's limiting efficiency at the moment is that the OLEDs, I think I haven't got the right slide in this stack, but the OLEDs, the radiant excitance, so the watts per square centimeter coming out of the OLED as a function of current density going in, is significantly rolling off at these regimes, and that's partly because we've not yet optimized just the electronic properties of injecting these short pulses into the device. It's partly because the devices have some additional non-radiative pathways when you get to very high exciton densities, and so this is one of the targets in looking at this new regime of operating OLEDs, and where we think again there's factor of 100 actually possibly an easy win to have in better electrical engineering of the devices. So we think that in the certainly the tens of milliwatts per amp sort of slope efficiencies are absolutely obtainable in these devices, and that's one of the paths that we're on at the moment to try and optimize the engineering of the full device.
Excellent. And my final one, and I'm sorry about this, is like you electrically driven, your LED in order, to pump, your gain media in order to have a lasing. And I was wondering, like, tuning the current source, finely tuning the current source that drives your LED does not lead to any fine tuning of the outcome wavelength?
No, because there could have changes arising from thermal changes in the device, but on the whole, no, the grating period is rather strongly clamping the device wavelength to determine what that is.
And the polarization that you receive on the as an output beam, is it defined by the orientation of the grating lines, or by the not by the semiconductor, not by the organic semiconductor?
No. It's defined by the grating. So it's very strongly polarized along the grooves of the grating.
Thank you. And you have never tried to pump, in order to lower the losses to the triplet state, to use femtosecond laser pulses, because you mentioned nanoseconds, and you did not move, to.
We in other experiments we've in particular been looking at strongly coupled microcavities, strong light matter coupling to make polariton lasers, and those we so far have always used femtosecond pumping. If the rise time of the pump pulse is of order 1 nanosecond, then it's okay. If the rise time of the pump pulse is of order 10 nanoseconds, it's less okay. But trying to deal with these triplets is another big target, and in some ways probably is the biggest target. The next really big exciting thing in organic lasers is to drive these into true continuous wave regime of operation, and so there are some organic semiconductor materials where there's a lot of work in the OLED context on managing triplet states, and we have some thoughts about how we're going to try and do some materials engineering that controls the photophysics in the gain medium to try to get away from some of that constraint. But this constraint on triplets has been an organic laser problem for 50 years, and is the reason that conventional organic dye lasers flow the dye molecules through the gain medium, through the cavity, because you're constantly trying to replace with fresh material that hasn't built up triplets. But we think that there are strategies to do better, and maybe to do well and get to full CW operation.
Excellent.
That's something that we're excited to be working on.
Thank you, Graham. Thank you very much for your answers and for your presentation. Do we have any more questions? So I think that I covered. I did too many.
I think you've given me a grilling, Costas.
So Graham, thank you again. I hope to meeting you face to face soon in Crete. You're very welcome to come and visit us whenever you want with your family.
We have blue skies, but it's 35 degrees colder than last time I was in Crete, and so.
So thank you, and I would like to thank all the participants, and we're going to upload the recording in our YouTube channel. So thank you very much, Graham.
My pleasure. Thank you very much. Bye-bye.
Bye.